This video will guide you through the configuration process of 3D trajectory recognition and simulation, which is commonly applied in industrial scenarios such as gluing, cutting, and grinding. Here, we'll take wheel hub grinding as an example. In this scenario, the robot needs to continuously grind along the outer edge of the wheel hub to remove burrs. Therefore, it's necessary to first recognize the wheel hub and then generate the trajectory based on the recognition results, thereby guiding the robot to complete the grinding. The configuration process mainly includes point cloud preprocessing, target object model and trajectory point generation, 3D recognition parameter configuration, output port configuration, and trajectory simulation. Point cloud preprocessing is used to filter and denoise the point cloud captured by the camera. It eliminates irrelevant point cloud to improve the target object recognition efficiency. During the target object model and trajectory generation stage, the object point cloud model and trajectory points can be generated in the target object editor as the reference path for robot execution. When recognizing the target object, select the matching method and adjust the parameters based on the object features. Make sure the object is recognized accurately, so that the trajectory can be generated accurately. After recognition, configure the output ports as needed to transmit data to the robot for subsequent trajectory tasks. Finally, the simulation function is used to verify trajectory posture, reachability, and potential collisions, ensuring the robot can safely execute the tasks. In this workflow, the steps on the left focus on target object recognition and trajectory generation, which can be completed using the 3D trajectory recognition tool. The step on the right are used to view the robot's grinding simulation results and verify whether the trajectory execution meets expectations. Now, let's enter the specific operation. Before starting the configuration, make sure the following hardware and software preparations are completed. First, select the camera installation method based on actual deployment conditions, such as the camera's field of view coverage and the target object size. In this scenario, adopt the eye-to-hand installation method. Second, select and install the actual tool based on the process requirements. In this scenario, use the end deburring grinding tool. Third, prepare solutions including Mech-Vision and Mech-Viz projects, and ensure that the tool model has already been configured in the Mech-Viz project. Fourth, connect the camera and complete extrinsic calibration. Now, start the configuration process. Open Mech-Vision. Enter the project interface and find the 3D trajectory recognition step. Click Config Wizard to enter the configuration interface. First, preprocess point cloud to eliminate irrelevant background and improve recognition speed and stability. Click Set in Set Recognition region. In the visualization region on the left, draw the 3D ROI of the object. The ROI should cover the whole object and exclude background noise, with a certain margin left around the edges. After drawing, click Save and Apply. You can check the point cloud recognition results in the visualization region. After confirmation, click Next. Then, generate the object model and trajectory. This helps to quickly obtain the object pose and trajectory during subsequent recognition. Click Open Target Object Editor. Since wheel hub recognition relies on precise point and surface feature information, and the STEP model matches the object well, select Import STEP file. While the system automatically converts it to STL for display, it utilizes the STEP features to generate a more stable point cloud model and trajectory. Enter a target object name and import the wheel hub's STEP model file. Click OK. Then, choose a proper unit. Once completed, choose a point cloud generation method to facilitate the subsequent generation of models and trajectories. In this scenario, it's recommended to use Auto-Generate Point Cloud. This quickly generates the surface and edge point clouds in high efficiency. Click Next to enter the Edit Model step. No adjustment is needed in this interface. Directly click Next to enter Set Trajectory. Here both Auto Create and Manual Create methods are provided. Generally, if there is a model file, Auto Create is recommended, otherwise, Manual Create is recommended. In this scenario, the STEP model file has already been imported, and the edge of the wheel hub is regular and clear. Therefore, use Auto Create. With this method, simply click on the model edges, and the tool will automatically recognize them and generate trajectory. Compared to manually picking points one by one, Auto Create can significantly improving configuration efficiency. First, set the picking settings, including direction settings and merging settings. Before setting, hover the mouse over the target edge to preview the tool Z-axis and the trajectory orientation. This helps you check if any adjustments are needed. Then, select the tool direction as either perpendicular or tangent. This parameter defines the initial orientation of the tool's Z-axis relative to the trajectory surface. Please note that since the trajectory is formed by the intersection of two planes, the initial direction of the tool's Z-axis is affected by the mouse movement path. Therefore, the initial Z-axis direction at the same trajectory may vary. The system will automatically generate the corresponding Z-axis direction based on which source plane the mouse moves from. Adjust the settings based on the actual process requirements and the preview results. In this scenario, the end edge of the grinding tool is used for grinding, so based on the preview results, select Tangent to ensure the tool's end edge fits the trajectory perfectly. Additionally, the visual preview shows that the Z-axis is currently pointing downwards. This means the tool would grind through the hole from the bottom up, which doesn't match the actual application scenario. Therefore, open Generate Opposite Tool Direction so that the Z-axis orientation is flipped by 180 degrees, allowing the tool to approach the edge from top to bottom during grinding. After that, open Auto Chain when picking trajectory. This function automatically merges adjacent segments into one continuous trajectory with a single pick to save time and effort. Next, pick the trajectory points. Use the left mouse button to click the edge of the object for picking. After the trajectory is generated, adjust the number and distribution of trajectory points as needed. In this scenario, keep the default settings. If higher efficiency is required, you can also reduce the number of trajectory points accordingly. For details, please refer to the documentation. In this scenario, since the tool center point is set at the center point, the tool's edge can't fit the trajectory. Therefore, adjust the trajectory offset to shift the trajectory inward along the Y-axis for edge grinding with the end tool. Here, set it to 4 mm. In actual applications, the value should be configured based on on-site testing data. In addition, the actual grinding process in this scenario requires the tool to maintain a specific inclination angle relative to the surface. Adjusting Euler angle X to control the tool's tilt pose. Based on the actual grinding angle, it is set to -20 here. At this point, one trajectory has been successfully generated. Then, continue generating the remaining trajectories by following the same steps above. Before generating each trajectory, preview the relationship between the tool's Z-axis and the trajectory surface to ensure a consistent initial orientation. Now, all trajectories have been completed. Save the trajectory. At this point, you can enable the corresponding end tool in the tool list to preview the positional relationship between the tool and the trajectory. Click Update Target Object, the model has been applied for recognition. Next, determine whether 3D recognition parameters need to be configured based on the point cloud alignment in the visualization. Currently, there is an obvious misalignment between the white point cloud captured by the camera and the blue point cloud of the model. In addition, there are many over-recognized edges on the surface, resulting in poor matching performance. This may lead to large trajectory deviations, preventing the robot from grinding accurately along the trajectory. Therefore, close Auto Set Matching mode and configure an appropriate matching method manually. Since the wheel hub in this scenario has clear and fixed profile features, it's recommended to use edge matching for the coarse matching mode to enable fast positioning. For the fine matching mode, surface matching can be selected. This utilizes the rich surface point cloud data for calculation, ensuring that the model fits the object surface tightly and thereby eliminating height deviations. Click Run Step to view the recognition results. Currently, the white point cloud and the blue point cloud is highly aligned, indicating good matching performance. In addition, the confidence score of the recognition result is also high, so no further parameter adjustment is required. Click Next to view the generated trajectory results. Then, configure the output ports. By default, the tool outputs the object name and the object center point. To meet the robot operation requirements, select Trajectory Point to output the trajectory point list. After that, the system additionally generates trajectory point information ports for outputting trajectory point labels, names of trajectory lines and corresponding objects. These data provide the necessary support for subsequent robot trajectory operations. At this point, the object recognition and trajectory generation are completed. After saving, make further step configuration based on practical requirements to output the results. Next, proceed to the simulation. Open Mech-Viz and build the simulation project according to actual requirements. The sample project here is only used for demonstrating the workflow, so only the essential steps required to run the project are retained. The first step is Fixed Point Move, which guides the robot from the initial position to the preset operation starting point above the wheel hub. Visual recognition is used to trigger the Mech-Vision project operation and pass the vision results to the Mech-Viz. Vision Move, trajectory, plans the robot's grinding trajectory based on the vision results returned from the vision project. Relative Move is used to lift the end tool away from the object after trajectory grinding is completed, preventing collisions during subsequent movements before proceeding to the next step. Finally, another Fixed Point Move step guides the robot back to the initial position. Among these steps, the parameters of Fixed Point Move, Visual Recognition, and Relative Move can be configured normally according to requirements. The following section focuses on the configuration of the Vision Move, trajectory, step. First, select the corresponding Mech-Vision project to obtain the trajectory recognition results. Then, select the trajectory source to determine which trajectories from the vision results will participate in trajectory planning. Since all trajectories of the object need to be ground in this scenario, select Use trajectories from selected target object, and then select the corresponding object for trajectory from the target object editor under Select Target Object. You can now see the object in the 3D simulation space. However, it's currently in its default pose because it hasn't synced with the vision recognition results yet. Please click Simulate to run the project. The accurate object pose will be automatically obtained and updated. After obtaining the object pose, enable Approach and Departure settings. This parameter can be used to add auxiliary path points before and after the trajectory to improve trajectory smoothness and operational safety. Finally, enable Lead-In and Lead-Out settings. This ensures the robot enters and exits the grinding area smoothly, further enhancing the grinding quality of the wheel hub edges. After completing the parameter configuration, click Simulate to check the running result. Now, the configuration of 3D trajectory recognition and simulation has been completed. For more configuration operations, please refer to our documentation.